Hello and welcome to Gotham Sound TV. Today's topic is RF distribution. And welcome to our Facebook Live viewers. This is an experiment, or that is to say our first time going to Facebook Live, so fingers crossed. Today's topic is about RF distribution. And we're going to talk about three different use case scenarios. We're going to talk about bag use, cart use, and we'll talk about a reality TV show type setup. The fancy term is distributed antenna system. I wanted to do this topic because it's something that we do here at Gotham Sound, and I have been involved in a lot of the setups that we do, and in all of these use case scenarios. I am by no means an expert, but I've had the good fortune to learn from experts, and I welcome your comments. I welcome the discussion. So let's jump right into it. Let's start with bag type setups. And, you know, we'll start with, well, here is, I don't have my diversity antenna, but, you know, typical receiver, ENG receiver, and, you know, it would typically have two antennas. It's okay. And that's fine if it's one or two or three receivers, four receivers, but when you start pushing up above four receivers, you really should start to think about, instead of having just a bunch of receivers stacked in a bag with all of their antennas, you know, less than an inch apart, you should start to think about separating that out. Why? So I think we have to talk a little bit about RF theory. So one of the issues when you have a bunch of receivers with their antennas really close together is in order for a receiver to receive a frequency, to be on frequency, it needs an oscillator of its own. And in an ideal design, the internal frequencies will never become external frequencies, but receivers can become very, very small transmitters. And those frequencies can interact with each other when the antennas are in a bag very, very close together. So if you imagine this was the next receiver, you know, would be stacked up right next to each other. Those receivers, even if they're coordinated, those antennas can start to interact, those frequencies can interact. And so you can really clean things up by going to a common antenna distribution. Now, we get asked, you know, a lot, well, and I don't have one handy, but, you know, a BNCT. Why can't I use a BNCT? I appreciate everybody looking around to see if we happen to have one here, but anybody, we can all imagine a BNCT. Why can't I take, you know, and we'll get into this, we'll get into this, but why can't I take a rubber duck antenna and run some coax cable into a BNCT and just split my antennas that way? And the answer is that in order to do that, you really, if you're going to use a BNCT, which I don't recommend, you lose isolation, right? So when you have multiple receivers in a bag, antennas not isolated, when you use a BNCT, BNCT is totally passive and completely bidirectional. It'll pass signal in any direction. You still don't get the isolation between receivers that you need. And so that's when people started to use splitters like this. So this kind of a splitter provides isolation. And this is an important building block. But for bag use, when you're dealing with multiple receivers, you really want to start to get into products like, we have this example here of the PSC RF multi-SMA, which will take 2 antennas in and split those 2 antennas to multiple RF outputs. And you also have the ability to turn on power and power the antenna there. That's the PSC RF Multi SMA. And then there's another product that's relatively new to the market. This is made by Audio Wireless. It's the model DAD M226. This adds not just RF distribution, but it can distribute power through these antenna inputs to receivers. Some receivers can actually take power through the antenna inputs, but also it can power auxiliary products that way as well. So these are 2 examples, and if we can show Alex Ramirez's bag, Jared. So that is a bag courtesy of Alex Ramirez, where you can see the RF distribution, and he's using a Zaxcom receiver, Zaxcom recorder, Zaxcom distribution. It really cleans it up. If we look on the left and right-hand sides, you can see the SNA antennas feeding the splitter, and yeah, it's feeding those 3 receivers via RF distribution. Doing this will give you increased isolation, and just by doing this, yeah, you'll dramatically increase the range, depending on the environment. Just by cleaning up the receiver antennas. It's hard to assign numbers, but you know, I would say a 10 or 20% increase in range is not an unreasonable expectation, depending on the RF environment. And yeah, I think while we're at it, if we can show Alex Ramirez's bag, let's talk about antenna width spacing. The ideal theoretical spacing is, you know, if we wanted to break it down into the RF theory, I would say it's half a wavelength, depending on the frequency. But practically speaking, if you can get it far apart, as far apart as your bag, then that's a great thing. I think what he's done is he's clipped the SNA antennas to the side of the bag. That's perfect. It keeps it nice and tight. Another option is the RF Venue diversity fin antenna. But yeah, anyways, have a look at that. And that combines a shark fin with a dipole in one small space. So that's a typical bag use scenario. And that's a great way to go about that. And again, you know, I think, you know, for Zaxcom, it's above 3 receivers, 3 stereo receivers. But when you start getting above, you know, 4 and above, I would definitely consider RF distribution for your bag. I think it's also an opportunity to talk about the idea of wideband. So one of the things that both of these devices do to one degree or another is offer some kind of cutoff. The PSC is actually pretty wideband. It says its frequency range is 470 to 870. One interesting feature of the Audio Wireless is that it has a, you order it at the factory, but basically it will come pre-configured for a filter that you have specified at the time of order. So that brings up an interesting topic, which is, you know, there is definitely a tension with wireless mics. The idea of going wideband is really, really great, and it's necessary, but it is possible that also when you go to such a wide bandwidth, you're bringing up the overall RF energy into the system, and that's not always good. You know, I think picture a walkie-talkie's RF energy. You know, that might be close to a block 470. You need some pretty hard filtering in order not to overload the front end of a receiver. And I think that's a good opportunity to talk about the nature of what's going on with RF circuits. So RF amplifiers, which are in all of these components that we're going to talk about today, all of the active ones, you can think about that as a kind of very, very tweaky mic preamp. And what I mean by that is that, if we think about like a really good amplifier, the more energy that you put into it, the more energy you get out of it. And it's in a perfectly linear fashion. If we were to draw a graph, it would be a straight diagonal line. What happens with RF amplifiers is you get to a certain point, you get more energy in, more energy out, and then you get to a certain point and it goes nonlinear. And you just get harsh, harsh, harsh distortion with all of the intermodulation distortion that goes along with any amplifier that saturates. And with RF circuitry, that happens very quickly. So one of the themes of today's discussion is going to be less is often more when it comes to RF. All right, so I think that covers bag use. If there's any questions, by all means, people chime in. But that's pretty much it for bags. Those are two products that I know of. You can certainly use these splitters. These Lectro distributes these, but these are from Mini Circuits, to make your own RF distribution for any use, but for bag use too. This is 1 in and 4 out. And this does provide sufficient isolation. And you would obviously need 2 of these if you were going to use diversity. The splitter won't provide power to antennas for the amplifier and antennas, though. All right, so let's talk about cart use now. So cart use, very often is, the RF distribution for the receivers is built in to a system. So like if we have a picture of the Venue 2, that would be an example of multiple receivers that have, a single pair of RF inputs get distributed to 6 receivers, or the Zaxcom RX12. So that is, again, 2 antennas in, A and B, and 2 6 receivers, or for them it's 6 stereo receivers, so it's hence the 12. Yeah, same idea, and that can be used for cart. But I think now is a good time to talk about, when we talk about RF distribution, we really have to talk about what's known as a link budget, and we have to start to think about how much RF gain is in our system. So Jared made an animation for us, and typical use case scenario for a cart, we have a power meter down below. There we go with our transmitter in perfect free space transmitting, and it's full power, but let's look at what happens. We start to move through air, and the first thing that happens is it gets put on a big bag of salt water, aka our actor. Shakespearean, I think. And then that knocks the power down, probably more significantly than that. And then our RF signal gets in the bunch of, gets into some trees there, nice thick moist foliage, and our RF power goes down. And this is where our link budget comes in. We're trying to get enough RF signal to our receiver for it to receive an acceptable amount of signal. And we'll talk about that in a second. But so the first place in our distributed system, in our antenna system, is the antenna. And that antenna all by itself, just by virtue of being a shark fin, provides some gain. So that knocked the power up, but then, wait a minute, it went through some coax, and through the coax it knocked the RF power down. And then it went in through our splitter, and our splitter has losses. And so that knocked our power down even more. So we're looking to provide enough gain so that our receivers receive an acceptable signal. By the way, our animation is only showing one side of a diversity, so we're just simplifying it there. So how do we do this? We come up with an amplifier, and in our amplifier, we're going to put it in the first place that we can make up the loss of signal between the cable and the antenna. And we want to set that amplifier not for its maximum setting, but for just enough to overcome the losses of the cable and the splitter. And that's really the key to this, is where we don't want too much gain. Thank you, Jared. We don't want too much gain because too much gain, remember when I was describing the nature of RF amplifiers, it's not just the power of our desired signal that can make an RF amplifier go nonlinear. It's the nature of the undesired signal, which is also, aka the noise, that can make an RF amplifier go nonlinear. And that's why wideband is not always necessarily a desirable thing. And that's also why we don't want to just increase the gain arbitrarily. We did some makeshift tests here in the studio, and I think this is where we start to talk about filters and antennas, because you really can't talk about distributing RF without talking about antennas. We did do a more in-depth discussion of antennas on a previous live stream, which we'll have a link to in the text of this. But let's talk about some typical antennas. Obviously, there's the rubber duck antenna. And rubber duck antenna is great when it is connected to something that can provide a counterpose or a ground plane. So that's what the metal on this receiver is doing. But it does not work when you just put it at the end of a coax cable. So we get lots of questions like, can I just use a T and not a T, a barrel, and just kind of connect it with a barrel to the end of a coax cable? But there is no ground plane, so you will receive some things, and if you are dealing with very, very, very strong RF, this might be a way of dealing with it, but it's definitely not recommended practice. What you need is an antenna with some kind of built-in ground plane. And that's where things like the SNA antenna come in handy. Yep. So that's what this is, or a folding dipole. It's also where these shark fins come in handy. They have directionality, and you can also use that directionality to your advantage. They're sensitive in the front. They have gain in the front. They have rejection along the sides. And you can think of it exactly like you think of a shotgun. And just like how you might orient a shotgun in such a way to pick up your desired signal, but orient the side of the shotgun to reject the noise, you can also use a shark fin in that way. And similarly, you would also, for example, if you were doing a shot downtown New York, or in any of the major urban areas, or pretty much anywhere where there's a transmitter, if your desired signal was the transmitter, but behind that transmitter was a huge broadcast tower, you might want to orient the antenna in such a way that it rejected the tower but got the desired signal. So that's part of RF distribution. The other thing I want to show is we did some tests in the office with our spectrum analyzer, and here's an antenna that is a really interesting design. It's not appropriate for every situation, but it's the RF venue spotlight antenna, and it is basically designed for near field applications, right? If one of our themes is less is more, this is a way to get less. Now, if you go to RF Venue's website, they have a great, an absolutely great comparison that they did in Central Park for Shakespeare in the Park, showing their antenna. But we did one here in our office to show you. So this is, we had a walkie queuing, and let's go to the previous one, Jared, from this. Yeah, so this is the Betso Sharky. We had it set to, here's the Betso Sharky. We had it set to 6 dB of gain. Betso Sharky is really a nice antenna because you can dial up the gain. And in fact, while I'm talking, I am just going to rig this up so we can actually see it work. You can dial up the gain on the antenna, and I think that that's a really great thing. So here, if anybody's curious how I'm doing this, I am going into this PSC multi-SMA. I'm going to rig up this antenna. And yeah, there we go. I'm going to turn on power, and when I turn on the power, yep, this becomes hot. So this was as we left it at 6 dB, but you can actually dial the gain up or down. You sort of hold it, and then you can dial it. And interestingly, this can go to negative numbers. So in that case that I was describing earlier, where you have a huge broadcast tower that you're in the vicinity of, that might be a super helpful thing to be able to do, to dial the gain down. So let's look at the first slide. Yeah, so this is our Sharky antenna plus 6 dB. We can see on the left that spike is a walkie cueing. That's part of the noise, and you can see sort of the baseline noise floor. You know, I would say averaging minus 74 dBm. And our electrotransmitter on the right, it's denoted M2 at minus 24.6 dBm, very strong signal, significantly above the noise floor. That would make a great reception, but also look at the noise floor. Remember, we're trying to maximize our signal and minimize our noise. So let's see the second slide, Jared, please. Noise floor drops considerably. Interestingly, our desired signal actually goes up because that's sort of the way that this antenna is designed. The close signal gets received very well, and farther away signals don't get received as well. So noise floor goes down, and even our walkie signal goes down a little bit. So that's an example of less is more, and that's sort of my design philosophy when I start to think about this stuff. You know, I think it's also worth noting that there are different kinds of coax cables. So in our animation, we showed how the RF loss goes down when the signal goes through cable. The different kinds of cable have different losses depending on the frequency. And it's always going to be a trade-off in terms of cable. The thicker the cable, the less the loss through the cable, in general across all frequencies. But the thicker the cable, the more of a pain in the ass it is on set. So that's going to be a balance. And I think it's a fair trade-off if you're going to set the amplifier at the antenna, you know, and you need to use slightly thinner cable because you're you're needing to coil it up and pay it out and coil it up constantly. That's going to be part of the equation that you think about. And then also to just kind of talk about different modes of RF distribution, both Electrovenue and this device, they have unity gain in theory. So you know, the signal coming in here, you know, like we said, has loss, because inside of this is really just a splitter. It's an 8-way version of this. But there's also an amplifier in here that overcomes the loss. So the inherent loss in the 8-way splitter. So just to wrap that thought up, signal coming in here is going to come out at the same level because the amp is set to unity gain. So your job in sort of coming up with a design is, when you choose an antenna, you set the gain based on your anticipated losses through the cable. So yeah, unless you're using a totally passive splitter, in which case you'd set the gain of the antenna to overcome the loss of the cable and the loss of the splitter. Okay, so cart use, you know, multiple antennas. are a useful tool to have. Directional antennas, but using the directionality, using the gain is a very, very useful tool for you. Even sometimes, like if it's in the middle of Midtown and your talent's not moving, and you're in Times Square, to be a little New York-centric about it, you know, this RF venue spotlight antenna, that you could put that underneath them, out of shot, and that becomes a really viable option. I know a couple of mixers have used this when they're shooting up on a rooftop, for example. Lots of RF energy, ambient RF energy, noise, but if the talent is near this, this is a near-field antenna, and it's going to pick up those signals. So, you know, you really have to think about, you know, antennas as part of this whole system. Okay, so we'll move on to the last use case scenario, which is, you know, the fancy word for it is a kind of distributed antenna system. You know, this is going to be the kind of rudimentary use of it. So we drew a typical sort of diagram of what a reality show might entail. This is a cooking show, and I made it a cooking show because there's some specific stuff I want to talk about. But you know, you have these contestants cooking here, and you know, there's some like pantry and pan storage here, hanging metal pots and pans here that they have access to. Here is a judge's table. And then, you know, maybe 50, maybe 150 feet away, you know, they have a stew room. Stew room is one of my favorite terms for in a reality show that I've learned, which is that's where the contestants go and stew while they are being judged. So you need RF coverage in these spots. So, you know, how do you begin to break down, you know, what you're going to do? So, you know, first of all, the way I think about this is in terms of zones. And I think about it, you know, as if it was not diversity at first. So just to think about where can I start to break up the action? And then I start to think about the diversity. Okay, so low-hanging fruit. The stew room, that's one zone. So I might put a pair of antennas in the stew room. So that's my two antennas. I might put them in opposite quarters. I might put them here. You know, I really have to see what's in the stew room and where people are congregating. You know, that's where these, if we can cut out to these folding dipoles, or also, I hate this term, but they're the Shure pipe bomb, they're wideband antennas. They both have roughly donut-shaped pickup patterns. But yeah, you know, so either in the middle there or in the corners, I would actually probably go with the middle there. So that's one zone. And let's call that, because it is the kind of less important zone, we'll call that the C zone. I realize I'm working backwards. So now we get into the meat of the issue. So we have the contestants all here. We have the judges' tables here. We know we need some coverage here, right? And definitely, you know, people walk up to the judges' tables as they're being judged. This is a very hypothetical diagram as a kind of amalgam of scenarios that I've come across. And we need coverage here. So one of the things that I notice right away is, you know, cooking shows, there's a lot of stainless steel. And stainless steel bounces around RF. And so now I think it's, you know, we start to talk about how we're going to handle that. What's the optimum way to get my desired signal in terms of the optimal antenna choice? And personally, I've had great luck with these PWS circularly polarized antennas, professional wireless system antennas. These are really, really fantastic antennas because when we talk about how RF propagates, if we have a transmitter, and it's attached to somebody, and the antenna is up and down like this. It's vertically polarized like this. The RF energy is being transmitted with a vertical polarization, and we want our receiver to match. So in a perfect world, both antennas would be vertical, and that's sort of the best way to handle that. What happens is RF energy bounces around, and particularly with hard metal surfaces, is that polarization starts to change and rotate into all directions. And that's where the circularly polarized antenna, which is sensitive to RF energy and with multiple polarizations, comes in handy. I think we have a diagram to kind of show. Yeah, this is sort of showing polarizing filters, but it's a similar idea. If you look on the left of the diagram, our RF energy sorry, let's look on the right of the diagram. It's unpolarized light. It's all, and in this case, light and RF energy we can think of as similar. On the right-hand side of the diagram, it's RF energy in all directions. And if we have something that's sensitive to only one polarization, then literally a whole bunch of energy is wasted. Whereas if we have something that's sensitive to all polarizations, then we can capture all of that energy. And so I find that really handy. So I would start to, I might start to put antennas here, down this area for one antenna, and down this area. And that gets people here. And then I actually, in terms of thinking about sensitivity, I might either use the RF venue spotlight antenna on the judges table, or I might use two antennas that might be dipoles here and here. But I think I would actually use the RF spotlight. So that leads us to an interesting question, which is how do we combine these multiple zones of RF into two diversity inputs of our receivers? And Jared, if we can show the PSC, yeah, there we go, the Multimax, thank you. If we look, this is a typical product. There's multiple manufacturers make products similar to this. Professional Wireless has their DB8 version of this. But if we look at this particular antenna splitter, if we zoom into the combiner, so this is 1-to-4 combiner, but it's also, we're going to use it as a combiner, and those 4 inputs on the top right there, those become our zone inputs. And so I start to split things off into diversity. Now, I would move these antennas out a little bit more, like that, because I want as much separation as possible, but I want to keep it away from reflective surfaces. So that becomes what I would call my C zone, and in my diversity 1. And that becomes my C zone in diversity 2, the second diversity input. This judges table right here, if that was one RF spotlight, that might be my B, and I might put that into diversity 1. And my 2 antennas that are pointed that way, and really it's, it might be wider band this way. It's the kind of pickup is that way. Those would be A1 over here and A2 over here. And so that would be how I would start to hook things up. If we flip back to the PSC, the close-up of the zone inputs, all of my ones would get hooked up to this left-hand side here. Sorry, on the PSC Multimax. This particular side of the diversity. And then we don't have a close-up of the right, but if we go to the full picture, yeah. Splitting to the other side, all of my 2s, C2, A2, and there is no B2, would get hooked up to the right-hand side of this combiner. So now, oh, by the way, every unterminated input or output would get a 50 ohm terminator on it. It's just best practice. So now we can start to calculate, well, what is the cable run? Where is the control room? The control room might be way over here. So what are these runs start to look like? Let's say I can start to make notes about my antennas and about their runs. A1, A2. So, this run might be 125 feet. This run might be 125 feet as well. B run might be 175 feet. And C2, might be 220 feet. And that's when I start to think about what cable can I get away with? What cable can I get away with? I need, it's an install. It's a cooking show. Do I need plenum rated cable? What's the thickest amount of cable that I need? What losses can I tolerate? That's when we start to look at, cable like LM400, RG8, sort of cable where flexibility is not really an issue. And I start to calculate the losses of the cable. We'll put up a link to a table in the text that shows how to calculate the losses for cables. And then that lets me set the gain of my amplifiers. I would put amplifiers like in the animation, either it would be like this kind of amplifier that's connected to the antenna already, or it would be a separate amplifier. Could also be set like the Lectro ones have jumpers, the UFM 50, start to really set my amplifier gains. Also, it's where I start to have my frequency band plan. And so I can start to think about how I would filter a lot of this so that I'm filtering out the undesired, the noise, basically, the undesired signal, which could include wireless hops to camera, IFB feeds, intercoms, all kinds of things. These devices are super handy to have around. Lectrosonics PF50 filters, and they come in 2 block-wide increments. And so if you can do your band planning, meaning your planning of wireless frequencies around those bands, you can start to put these in line before you even go into that combiner. And Jared, if we can show the PWS unit, that would be cool, because the PWS unit does have a pretty cool feature. There it is. If you can see, those switches for each input can dial up attenuation. So, for example, if we flip back to my diagram here, the contestants are not always going to be in the stew room. And so when they're not in the stew room, I can set that attenuation to the maximum so that it's not just adding RF noise. Similarly, I can start to balance out the noise between all those antennas using the PWS. Both of the PWS and the PSC units will provide the power for downstream amplifiers. That's called bias power. And I think, I'm happy to take people's questions, but we've covered a lot of ground. We're at the 40-minute mark, so I think we ought to wrap things up. Yeah, Joe, did I miss anything? Is there anything?
We got a couple questions. One is, would a spider antenna be good for a compact plant antenna?
A spider antenna. I don't know what a spider antenna is.
That's from Andrew Jones.
I don't. Andrew, what is it? Is it? I wish it sounds like a cool antenna. It sounds like something I should know. I'm hoping it's a colloquialism for an antenna. But yeah, I mean, I think if you can plant an antenna and get close to your desired signal, that's going to be good. You know, RF output power and link budgets also go to setting your transmit power. So if you're really on top of your talent like that, that's also an opportunity to turn down your transmitter power, so you're not overloading that amplifier in the receiver. Any other comments or questions?
Emilio from Argentina, who says hello, asked us about changing the EW100G3 antennas by removing their original antenna,
yeah,
and changing it with an SMA coaxial connector.
So I think if you, first of all, I really like the G3s. And I think that if you have a lot of them in a bag, like if you're using 4 or 5 of them, I would totally do that mod. And that's when that opens up the possibility of using multi-couplers. Yeah, and I think that that's a great mod for that. You know, at some point you reach the sort of tipping point of whether it's worth it to get a receiver with a native SMA connector. But yeah, I mean, if the mod is within your means, then it's a good mod. Anything else? I know I've skipped over a bunch of stuff, and I hope that you know, we'll be able to further this discussion, maybe do a follow-up. But I appreciate the opportunity. This has been a kind of, like I said, an amalgam of many questions and conversations that I've had. And yeah, thanks for watching. Next live stream is Tuesday, March 21st, rain protection. Yeah, beware of March. In like a lion, out like a lamb, is that what they say?
Close.
Close. In like a lamb, out like a lion?
I think it's April and May.
Oh, yeah, all right. Well, anyways. But anyways, March 21st, rain protection, Gotham Sound Expo, May 13th. Actually, I'm excited about both of those. I'm especially excited about the Gotham Sound Expo, May 13th, in our shop here in New York. We are going to have upwards of dozens of manufacturers. Dozens? 2 dozen, 20. Yeah, close to 2 dozen manufacturers and growing here in our shop. Saturday, May 13th, so look for 11 a.m. to 4 p.m. Here in the shop. And as always, our archives are at gothamsound.tv. Follow us on Facebook and Twitter, and please send your ideas for live streams to info@gothamsound.com. Thanks for watching.